out in the camera.
Okay. So thanks a lot, Roberto. Thanks to Sojay for inviting me to come here to this conference, which is very interesting and for this year is coinciding with the G7 on transport, which has just started this morning in Cagliari, and I think is very interesting event because for those of you who have had a possibility to see a preview of this G7 concerning transport here, there is a synergy between ERTMS and Galileo. So Galileo will be put on the agenda to be adopted for the ERTMS. So today I will talk about another application which is been already anticipated, is in the automotive sector, but starting from rail. And in order to start correctly my talk, I want to show you a slide which was presented by Joseph Doppelbauer, the director of IRA, a couple of months ago, indicating the need to innovate in the rail sector and showing also, as an example, the automotive and ICT sectors in terms of rate and of innovation and also order of magnitude of investments which are provided. Landscapes from benefiting of what has been done on rail to automotive has to take into account, first of all, what is the evolution plan of ERTMS in Europe. As you see here, the plan of ERTMS is to introduce the so-called RTMS level 3, which allows the elimination of trackside. So the communication will be done by IP-based networks, and satellite will be heavily used for the localization. So this is done in terms of plan, is ongoing, and is shared among all the stakeholders which are part of this game. On the other side, concerning the automotive sector, there are two say approaches ongoing. One which is I mentioned before, the connected car, which is a stepped approach, is what the car manufacturers are doing. So they innovate step by step. So the product is under control directly by them, and they introduce different steps of innovations. On the other side, the newcomers are looking to so-called robotized car. So it's completely different approach where they are defining a new paradigm to move people and what is around in terms of platforms. So these two roadmaps are ongoing, and all the industries, manufacturers and main players are involved. To summarize, what we believe is there is a synergy between rail and driverless car, starting with the RTMS, where the system is already able to supervise the train and to control the speed. We have the car where the technology today is making a lot of innovations, especially on sensors. All the sensors are involved. LiDAR, video, everything is under experimentation. And the localization must be accurate and safe, and the vehicle must react in real time. These new sensors are not the only innovation, because also the infrastructure is evolving. So the idea is to have these highly automated roads with possibility to communicate with the vehicle, and video GNSS positioning and federated augmented networks. Thanks, Mario, you have mentioned this, but I think we have not coordinated, but I think this is a positive synergy, because there are two applications, rail and automotive, where the federation of a unique augmentation network can give an economical advantage. And we can arrive more rapidly from a centralized control to the real autonomous control, hopefully also on the train. So there is a benefit. And in fact, the operator, RFI, who is integrating with ANAS, the operator of railroad, is highly supporting this synergy because of the reciprocal advantage they see. And maybe there is a room also for a new standard in ERTMS, because ERTMS is very well regulated and accepted.
I will introduce the RHINOS project, which is a project founded by GSA in the framework of Horizon 2020. And I will give you a short overview of the project and main achievements, because then we will have several contributions that will touch many of the topics that have been considered in the project. For those of you that have no information about the RHINOS project, let me say that this project is based on international cooperation between Europe and USA, and the partners of the project are Radiolabs, which is the coordinator, Ansaldo STS, SOJEI, the University of Nottingham, DLR, the University of Pardubice, and the University of Stanford. And after several projects that have been funded both by ESA, Trainsat, and GSA, RHINOS, just to mention one of the most recent, that were essentially focused on what we have on board of the system. In RHINOS, we were focused more on the augmentation network, on the overlay system, with the aim of providing support for AI techniques for integrated monitoring have also been considered, but the fact that we were focused on GPS and Galileo doesn't mean that we will not make use even of GLONASS of BeiDou as further constellations in order to have better performances. Let me summarize the main achievements that we had in RHINOS. First of all, we were focused on railway environment modeling, and essentially multibat was the thing that we are focused on. Then after modeling, we started to define candidate solutions for both the augmentation network, the onboard and onboard system, and as well as mitigation, detection and mitigation of the local hazard. Here you see a synthetic diagram of the system. We have on board of the train the advanced system for the monitoring of the integrity, which uses both the GNSS signal in space, which is received on board of the train, but even the output of the global hazard monitoring, which is provided by the augmentation network, and local hazard monitoring that comes partially from the unit on board and partially from the cooperation of all those trains that have been running along that part of the railway network. We also did the cost-benefit trade-off in order to select the best architecture among the different candidates that we considered, and we performed not only cost-benefit analysis, but even strength, weakness, opportunities, and threat analysis. Then, with respect to the selected solution, we considered a deeper evaluation assessment of the performance, which has been realized by means of a proof of concept that was using synthetic data, historical data, time series data, and even data that have been recorded on a real rail environment. And after realization of the proof of concept, we are now in the phase of verification of the reference architecture performance. And last but not least, the dissemination consensus sharing, and my talk today, and even of the other partners that will talk after me, are part of this dissemination activity of RHINOS. To show you some preliminary results that we had with real data, we used one of the reference stations that Sojei deployed in Sardinia. We used a septentrion receiver located on board of a train we used in the IGAW project, using a double frequency information on a GPS constellation. This is what I'm showing to you. On the left side, you have the mileage of the train versus time. So the train was running, sometimes it was stopping. And what you have in the right side is the posterior probability of each of the two hypotheses. The blue one is the correct one, the red one is the wrong one. And the scale, you see, is a logarithmic scale, otherwise you wouldn't appreciate the difference. And the probability of the wrong track never exceed 10 to minus 13. This doesn't mean that this is the probability of error. It's not a story. It's the value of the two ratios. And in the simulations that we performed with real data, we never had, even with single epoch, a fault. But the number of epochs is too small to claim more than 10 to minus 4, for instance. Just to be clear. So we have to make more and more experiments, validations. RTMS is not in the loop. He cares about that, but is absolutely a significant advance with respect to the state of the art that has been achieved in the RHINOS project. Just before getting the conclusion, let me say that the environment is prone to multipath. And on the left side, you have the geometry-free indicator, that means L1 minus L2 for one satellite. And you can see here the places where the multipath is present in terms of when you have tunnels or even small elements along the line. This is another satellite, one more satellite. You see different satellites in different points, have multiple in different points. Sometimes they coincide, at least for a couple of them. And so the data I was showing were from a real environment, but not with ERTMS in the loop. So going to the decision, the conclusions of the experimental activity confirm that is a good trade-off, exchange accuracy for ambiguity fixing, thanks to the wide lane combination and narrow lane combinations for code and phase respectively. And there is also a trade-off that has to be done between accuracy and the time needed to discriminate the track, because I showed to you the single epoch decision, but we can combine different decisions taken at different times altogether to decrease the probability of error. In that case, the correlation of multiple errors is quite important, and a good model is needed to avoid to underestimate the probability of error. And so temporal integration and multiple constellations are elements that can be applied to obtain a seal for compliance system which is not so expensive. And at the end, we can say that the opportunity that Galileo introduces with the civil signals in order to start to use 2-frequency, 3-frequency receivers that may cost no more than twice a single conventional receiver is really a good opportunity to solve challenging problems as the one that I presented in the second part of my talk. Thanks.
About the system architecture, this morning Sam has made an overview of the system architecture. We have the track side through the GBus local augmentation plus TALS trackside verification. We have the layer of onboard unit and an external layer made up of external network and SBUS ground services and GPS and Galileo ground services. That this layer is important because in particular SBUS ground services are the services provided to user through SBUS, in particular EDAS for RHINOS. GPS and Galileo ground services are the ancillary services provided to user for very high accuracy services. In particular, we know that we have IGS for GPS and GGSSP for Galileo. And we have an external network of reference stations. It's important that this network will be linked under the provision of a safety case certificate able to guarantee the levels of accuracy and integrity needed for the TCS operations. This information will go through a high quality of service security communication network. This layer is very important because we need to have low latency and a reduced number of lost packets. Then we have the radio block center layer. This is the track side layer, and it implements the GBus local augmentation together with the SBUS raw data and measurements coming from the SBUS layer. So we have the TALS trackside verification, that it is the architectural block that send an high integrity and augmentation data to onboard unit in order to calculate the position on train and to calculate the protection level according to a defined threshold, a defined alarm limit. So, which are the candidate augmentation architectures? The candidate augmentation architectures, we know from the state of art, we have the SBUS. The application domain for SBUS is aviation, and the accuracy that you can reach is smaller than 2 meters, and the integrity is equal integrity risk to 10 minus 7 for time to alarm of 150 seconds. Then we have the GBus and the local differential GNSS. The application domain is aviation and maritime. The accuracy that you can reach is lower than 16 meter, and the integrity that you can reach is between 10 minus 7, 10 minus 9 per 150 seconds. For AI accuracy services, we have the RTKey and network RTKey, in particular for surveying as application domain, and the accuracy that you can reach is smaller than 5 centimeter in ambiguity floating. Then we have the triple P, that it is suited for different application domains as surveying, maritime, and autonomous driving. The accuracy that you can reach is more or less 10 centimeter in floating conditions, or in ambiguity resolution smaller than 10 centimeter. The problem with these two techniques, RTKey and PPP, is that if you want to reach the requirements of integrity, you need to use the CRAIM or CRAIM techniques. But from this analysis that we made with SOJ and unsolved STS, we have achieved that no single system can currently meet the rail requirements, in particular about the longitudinal requirements. In particular, the maximum balise detection error needs to be smaller than 1 meter for vital purposes, and the tolerable hazard rate equal to 10 minus 9 per hour. Say considerations are valid for lateral requirements because the accuracy is smaller than 3 meters and the tolerable hazard rate equal to 10 minus 9 per hour.